is just data where I'm looking up the meaning of words, okay? So this is part 210, line 18t, Exciton, fret, radiative decay rate, short wavelengths, EET, Wow Seti. There's our alien radio signal there. Exciton quotes. So this is from Wikipedia. There's a picture for you to look at. Frankel exciton, the time dependence of the internal structure of the charge transfer exciton in LIF, created by an idealized point source represented by the wavy line. The absence of significant structural changes indicates that the relative motion of the electron and hole is frozen, which demonstrates that this is a Frankel exciton. And the credit goes to Peter Abamonte. An exciton is a bound state of an electron and hole which are attracted to each other by the electrostatic Coulomb force. Now, as you know, Coulomb force has come up before. Electron and black holes have come up before. So it's kind of interesting that all these words, see, quasi-particles, semiconductors, matter, transport energy. So all of this has something to do with our project. I don't know yet what it means, but we'll figure it out. An exciton is a bound state of an electron and hole which are attracted to each other by the electrostatic Coulomb force. It is an electrically neutral quasi-particle that exists in insulators, semiconductors, and some liquids. I wonder if it's in liquid argon gas. The exciton is regarded as an elementary excitation of condensed matter that can transport energy without transporting net electric charge. An excitron forms when a photon is absorbed by a semiconductor. This excites an electron from the valence band into the conduction band. In turn, this leaves behind a localized positively charged hole. Holes actually don't exist. The term is an abstraction for the location an electron moved from. They have no charge in and of themselves. The electron in the conduction band is then attracted to this localized hole by the Coulomb force. This attraction provides a stabilizing energy balance. Consequently, the exciton has slightly less energy than the unbound electron and hole. The wave function of the bound state is to be hydrogenic, an exotic atom state akin to that of a hydrogen atom. However, the binding energy is much smaller and the particle size much larger than a hydrogen atom. This is because of both the screening of the Coulomb force by other electrons in the semiconductor, its dielectric constant, and the small effective masses of the excited electron and hole. The recombination of the electron and hole, the decay of the exciton is limited by resonance stabilization due to the overlap of the electron and the hole wave functions, resulting in an extended lifetime for the exciton. The electron and hole may have either parallel or antiparallel spins. The spins are coupled by the exchange interaction, giving rise to exciton fine structure. In periodic lattices, the properties of excitons show momentum k-vector dependence. The concept of excitons was first proposed by Jakob Frankel in 1931 when he described the excitation of atoms in a lattice of insulators. He proposed that this excited state would be able to travel in a particle-like fashion through the lattice without the net transfer of charge. So Wannier-Mott excitons. In semiconductors, the dielectric constant is generally large. Consequently, electric field screening tends to reduce the Coulomb interaction between electrons and holes. The result is a Wannier exciton which has a radius larger than the lattice spacing. As a result, the effect of the lattice potential can be incorporated into the effective masses of the electron and hole. Likewise, because of the lower masses in the screened Coulomb interaction, the binding energy is usually much less than a hydrogen atom, typically on the order of 0.01 eV. This type of exciton was named for Gregory Wannier and Neville Francis Mott. Wannier-Mott excitons are typically found in semiconductor crystals with small energy gaps and high dielectric constant, but have also been identified in liquids such as liquid xenon. In single-wall carbon nanotubes, there we go. Okay, so carbon nanotubes are also mentioned in the space elevator, so I'm thinking this is another space elevator component as well. In single-wall carbon nanotubes, excitons have both Wannier-Mott and Frankel character. This is due to the nature of the Coulomb interaction between electrons and holes in one dimension. The dielectric function of the nanotube itself is large enough to allow for the spatial extent of the wave function to extend over a few to several nanometers along the tube axis, while poor screening in the vacuum or dielectric environment outside the nanotube allow for significant binding energies of 0.4 to 1.0 eV. Often there is more than one band to choose from for the electron, and the whole leading to different types of excitons in the same material. Even high-lying bands can be effective, as femtosecond 2-photon experiments have shown. So the next thing is fluorescence resonance energy transfer, FRET. Resonance energy transfer, RET, or electronic energy transfer, EET, is a mechanism describing energy transfer between two chromophores. Forster resonance energy transfer. Fluorescent resonance energy transfer, FRET, resonance energy, RET, or electronic energy, EET, is a mechanism describing energy transfer between two chromophores. A donor chromophore, initially in its electronic excited state, may transfer energy to an acceptor chromophore in approximately, typically less than 10 nm, through non-radiative dipole-dipole coupling. Dipole-dipole coupling's come up before. I don't know what it was up in the 170s of the line 17 videos, sorry. Anything between line 17 and line 18 has a lot of formulas and stuff in it, but dipole-dipole definitely came up before. This mechanism is termed Forster resonance energy transfer and is named after the German scientist Theodor Forster. When both chromophores are fluorescent, the term fluorescent resonance energy transfer is often used instead, although the energy is not actually transferred by fluorescence. In order to avoid an erroneous interpretation of the phenomena that is always a non-radiative transfer of energy, so it looks like there's no radiation created from this transfer of energy, even when occurring between two fluorescent chromophores, the name Forster resonance energy transfer is preferred to fluorescent resonance energy transfer. However, the latter enjoys common usage in scientific literature. FRET is analogous to near-field communication in that the radius of the interaction is much smaller than the wavelength of light emitted. In the near-field region, the excited chromophore emits a virtual photon that is instantly absorbed by a receiving chromophore. These virtual photons are undetectable since their existence violates the conservation of energy and momentum, and hence FRET is known as the radiationless mechanism. So we have quantum electrodynamical calculations have been used to determine the radiationless FRET, and radiative energy transfer are the short and long range asymptotes of a single unified mechanism. So it looks like this is the type of mathematical equation you're going to be using, these calculations here, to create this mirror that transfers light for the space elevator. That's the only thing I can think of. Theoretical basis, the FRET efficiency E is the quantum yield of the energy transfer, the fraction of energy transfer event occurring per donor excitation event. So there's the mathematical equation that you'll need to use. Ket is the rate of energy transfer, Kf the radiative decay rate, and Ki are the rate constants of any other de-excitation pathway. So you have a no FRET signal. And there you have a FRET signal. So this is the example of FRET between CFP and YFP wavelength versus absorption. A fusion protein containing CFP and YFP excited at 44 nm wavelength. The fluorescent emission peak of CFP overlaps the excitation peak of YFP. Because the two proteins are adjacent to each other, the energy transfer is significant. A large proportion of the energy from CFP is transferred to YFP and creates a much larger YFP emission peak. Okay? I'm glad you understand that, because I don't. It's a good thing. Obviously, it creates some sort of energy thing or something. Fluorescent principles, energy transfer, FRET, light emitted upon excitation by illumination at a shorter wavelength. So those are the keywords there. So this is getting very interesting. We're going to go on to our next video now, okay? Thanks for watching.